Welcome back to another physics lesson. Last we left off, we derived the equations of motion and learnt how to use them. And this lesson we're just going to build on that, and we're going to use these equations to analyze and describe projectile motion. So without further ado, let's get into it. First of all, let's start with defining what projectile motion actually is, which is essentially the motion an object follows when it's thrown or projected into the air without any energy or power source acting on it after the launch. Another thing to note is that projectile motion is typically characterized by having a parabolic movement path, so it'll look something like this. And this can be like a ball being thrown into the air, or a rocket being launched, or a golf ball being struck by a club. And when this object is launched in the air, it's typically got a velocity vector that is in the direction of the flight path initially, so it'll be something like that if I was to draw a velocity vector. And the only other force that acts on this object after it's been sort of released into the air is the force of gravity, which acts downwards. And as we know, gravity imposes a acceleration downwards, which is 9.81 meters per second squared, which will be constant throughout the entire flight path. So if I was to draw this with a bit more detail, it'd end up looking something like this, where the horizontal velocity would remain constant throughout the entirety of the motion because there would be no air resistance acting against it. However, the vertical velocity vector would decrease over time up till the point 3, up till its maximum height, which I'll label here as x max in the vertical direction. And that would be due to the gravity causing an acceleration downwards, which I'll put down as well. And that would be acting at 9.18 meters per second squared. So up to point 3, that gravity will decrease the velocity. Once it reaches the top of its flight path, you'll see that the velocity vector will start to grow again because it'll start to accelerate in the y direction but downwards. Now, me having said gravity acts at a constant 9.81 meters per second might have triggered some alarm bells because we've already got equations to describe motion that experiences constant acceleration. And we know these to be the equations of motion, which I've written over here. And what this allows us to do is actually break this motion up into two components, where we can describe the vertical velocity with the constant acceleration equations, and for the horizontal component we can just use our faithful v is equal to x on t, where v is the horizontal velocity and x is the amount of distance that's covered horizontally, or xh rather. So I can put that down there as well. Now what you'll find is that there are typically 3 types of projectile motion problems which you'll come across, and I've drawn these on the next page. The first of which is horizontal projectile motion. So let's look at that a bit more carefully. In horizontal projectile motion, the object will be launched horizontally only, where the initial velocity will purely be in the x direction, with the vertical component of velocity increasing over time due to acceleration caused by gravity. The flight time of the object undergoing horizontal projectile motion will be equal to the time taken for the object to hit the ground. So if we look at that vertically, we can use the constant acceleration equations to calculate the time. So if I'm looking in the vertical direction and I'm trying to calculate the time taken for this object to hit the ground, I'll call this xv, which is our vertical displacement, and I know our initial velocity will be equal to 0. Our initial vertical velocity will be equal to 0. So I can go ahead and grab this equation over here, and I can say xv, which is our vertical displacement, is equal to ut plus half at squared. And I know our u, which is going to be our initial horizontal velocity, will equal 0, so that term will go to 0. And I know our g is going to be gravity, So I can sub that in to say half gt squared is equal to xv. And if I rearrange this, I can find an expression for t. So I can say t is equal to 2xv times g squared. And that'll give us our flight time. And this same time can give us the expression for our horizontal displacement as well. Horizontally, we know that our velocity is not changing, so we can go ahead and use v is equal to x divided by t, where our x is just our displacement horizontally, so I can plug that in. And I know our v is just going to be the same throughout the motion, so the horizontal velocity will remain constant. And I can rearrange this expression for t, so I can go ahead and say t is equal to xh divided by vh. And that'll give us the expressions for the flight times, depending on what information I'm given in the question. So let's go ahead and actually attempt a question. So, let's say we have a ball that's launched horizontally off a cliff. And let's say this cliff is 80 meters high, and this ball here is launched at 30 meters per second, and we've got the force of gravity that's causing an acceleration downwards of 9.81 meters per second. And let's say we wanted to find out the following things. Let's say we wanted to find out the flight time, the horizontal displacement, which I'll label here as xh, and the velocity at the point of contact with the water. So what will this be? So let's see what information we've been given. And we've been given, so at the start of its journey, the ball is going to have a horizontal velocity only, and that'll be 30 meters per second. And our vertical velocity is going to be 0. So let's sketch that out using our coordinate system. So we got our ball, which is initial velocity will be 0, so we'll say u of v is equal to 0. We know the acceleration is going to be 9.81 meters per second squared, and we know the x in the vertical direction is going to be the height of this cliff, which is going to be 80 meters. We need to find the t, and we don't really know what the final velocity is, so we'll leave that as a question mark for now as well. Now this ball is going to be traveling downwards, so I'll make downwards positive, and I can go ahead and use this equation over here because we know that we're going to be experiencing constant acceleration, so I can go ahead and put my values in. I can say x of v is equal to u of vt plus half gt squared. That will go to 0 because our initial velocity in the vertical direction is 0. And I can rearrange this equation for t, so I can take everything to the other side to say 2xv divided by g is equal to the square root of t. So I'll go ahead and sub all my values in. So it'll be t is equal to the square root of 2 times 80 divided by 9.81. And I've just noticed that I've actually made a mistake in the last slide where I've derived the equation for t wrong, so I'll just go back and fix that real quick. So time should actually be equal to 2 times xv divided by g square rooted. So let's go back to our problem and let's plug these values into the calculator. And this will give us a value of 4.04 seconds for the time to hit the ground. So that answers part 1 of our question, and it gives us the flight time for this object. Now what if we want to go ahead and find the horizontal distance that's covered by the ball? Well, we already know the flight time is going to be 4.04 seconds, and we also know that the ball is launched horizontally at 30 meters per second, and there's no air resistance acting on the ball to slow it down. So we can refer to our earlier equation of v is equal to x divided by t, which is just our equation for constant velocity. So v in this case is just going to be the velocity horizontally, and x is our unknown, and our time is given as 4.04 seconds, which we calculated before. VH is 30 meters per second, so I'll sub that in, so it'll be 30, and x is going to be our horizontal, so I'll put that there, and I'll take 4.04 to the other side to find our XH, so I'll go 4.04 times 30. Now we put this in the calculator and we get a horizontal displacement of 121.16 meters. So let's move on to our final part of this question, and I'll label that over here. To work out the velocity that the ball hits the water with, we need to work out what the vertical velocity will be at the end of the ball's flight time. We know that the horizontal velocity will remain constant throughout the motion, but the vertical velocity will increase due to gravity. So we know that the ball is actually going to hit the water at an angle, where this is our horizontal velocity component, and that'll be consistent, and that'll just be 30 meters per second. And our vertical velocity component will increase over time, and that's going to be the thing we need to find out. So we can go ahead and use the same equations of motion that we did for part 1 of the question. So we know our u of v is equal to 0. We know our acceleration is equal to 9.81 meters per second squared. We know our distance is going to be 80 meters, or our displacement rather. We also know our flight time, which is 4.04 seconds. And what we need to find is v of v. So if I go back up to our equations of motion, there's actually two that will do the job, but I'll go ahead and use this one because it's easier. There's no squared terms in there. So I'll go ahead and plug that in. So let's write down our equation. V is equal to u plus at, where v is going to be our vv, final velocity of the vertical component. U is going to be 0, acceleration is going to be 9.81, and our time is going to be 4.04. I can put that in the calculator, and that'll give us a final vertical velocity component, which will be 39.63 meters per second. Now, in order to find our total velocity vector, all we have to do is use a bit of Pythagoras. So we can go vh squared plus vv squared square rooted is going to give us a vf, which is our final velocity vector. So I can go ahead and substitute those values. I can say v of f is equal to 30 squared plus 39.63 squared, and that entire thing is square rooted. And if we put this in the calculator, I get an impact velocity of 49.71 meters per second. Now we could take this a step further and also calculate the angle with which the ball actually strikes the water, but I'll leave that for another question. And let's move on to the next sort of problem that you'll see when we're discussing projectile motion.